Okay. So good morning, hello everyone. I think we haven't finished this part. So I think I'm going to go for finishing this part, and then the other sketch curves, and one other example, and oh yeah, I haven't attached the answer key for homework and the midterm. How about the midterm? The last year, yeah, last year midterm. Have you tried?
Yes.
Can you do all the questions or
I don't need to do the first part.
the first one? Yeah, I think because I haven't finished the chapter 4 because some of the problems we need to have a little bit knowledge on chapter 4, especially related to the optimization and the indeterminate forms, which we are going to, I think we are going to finish that by today for at least for the L'Hopital rule and the indeterminate forms. And tomorrow, probably the optimization. So if you can do all that, then next week we may have midterm. But I can adjust the schedule according to your preference. If you are having another exam next week, do you have any other exam next week? Or no?
Ministry?
When?
I think it's supposed to be on Friday.
Friday, this Friday?
Next week.
Oh, next Friday. If not, then the next 2 weeks also okay for me. Next 2 weeks, but we need to continue. Okay, we need to continue. But you can have your at least your TA giving you more exercise on preparing midterm. Do you prefer on Wednesday or Thursday? Wednesday means morning like this, or Thursday afternoon class.
Afternoon.
Afternoon. Yeah, morning maybe you haven't yet wake up. Yeah. Okay, I think that's. So, do you think it will be okay for next week for midterm or next 2 weeks? Next week.
In 2 weeks, yeah.
But in between, we need to move on. Okay, so we are going to have chapter 5. Okay, chapter 5. But for your TA class, your TA still can give you preparation for midterm. Okay. So if 2 weeks, then this week I can give you online quiz and also exercise on chapter 4. Maybe I will announce around tonight or tomorrow. Okay, for the quiz. So you have around 5 days to work. I think 5 days should be okay. The quiz will be chapter 3. Okay, let's continue for solving the sketching curve. This one. Okay, if you have any other suggestion for the midterm, please let me know. Okay. For now, I think for the one who are able to come now, prefer 2 weeks. I think still okay. 2 weeks. Okay, so continuing this part, okay, so we have these functions. So the next part is after we get the domain, intercept, symmetry, and the asymptote, what we need is we can check the, let me write again the functions. Then we try to take the first derivative. Okay, take the first derivative, we take the quotient rule. So 4x, x squared minus 1, minus 2x, and then 2x squared. Okay. We can solve this if you want, but we can also rewrite this as 2 plus 2 and we can also do the same thing for the derivatives. Okay. I think it should be the same, right? Should be the same. Either you go quotient rule first or the second one. This goes to be negative 4x. All right. So this is 4x cubed. Okay. And then the next, after we get the first derivative, we are going to check the first derivative test. Okay, we test the point, and if we get this, then x equals 0 is one way to get the critical number, right? So x equals 0 is probably our critical number, because when x is equal to 0, we are getting the f prime to be 0, right? So this is probably a critical number. So we can write here first. Okay, so we can take to the line number that's 0. But don't forget that we are also getting a vertical asymptote, right? We want the vertical asymptote, as we mentioned here, that we have 1 and negative 1. Okay, and also we get this when it's equal 1 or x equal negative 1, the denominator is 0, which means it will be undefined. So maybe we need, just to make sure that we are going to check the number in between this asymptote, or maybe the left asymptote, or maybe the right side of the asymptote. So we check the signs now. So we check between here. So maybe check negative half, maybe 2 here, negative 2. So if we check, this will be negative, right? And this will be positive. And if you put negative 2, that will be positive also. This is also negative. So it's going to increase, decrease. Okay. We haven't yet have any conclusion yet. For now, we need to check the second derivative. Okay. So we can take the second derivative. Let me write here. So we take the quotient rule one more time from the first derivative. So we take and make it and now it's become 4. Okay. And this will be negative 4 x squared minus 1 squared, and then minus, this will be minus 4x multiplied by 2 x squared minus 1 and multiply 2x. Let's solve that together.
So this will be negative negative 4 x squared and 4, right? And then multiply with x squared minus 1. Okay. Or maybe 16. Let me write directly 16. Okay. And then the next thing is I will factorize the x squared minus 1. So we are going to have negative 4 x squared minus 1 and minus 16 x squared. Okay. And then we can cancel this, right? Oh, this should be plus. Sorry, it should be plus. Yes. Yeah, minus become plus. Okay. Now this becomes negative 4x squared plus 16 is 12x squared plus 4. Okay. Okay, now what next? How to check? For every first derivative or second derivative, our instinct or our obvious option should be equaling to 0. Should be equaling to 0 to find out whether it has the critical number, or in our case here, whether it has inflection point or no. Okay. But equaling it to 0, it doesn't mean it will be our inflection point. We need to make sure that the concavity changes. So we need to make sure in the line number. Okay? Always check with the line number, checking the signs. Okay? So if we take this to be equaling to be 0, okay, if we take this 12x squared plus 4 equals 0, it is impossible, right? Every aspect from numbers that you can take to substitute this x squared is always positive, right? Because it has squared, right? So let me write it, it's always positive. So this always positive. Okay, but we are still able to determine when the second derivative is positive, when the second derivative is negative. Okay. How to determine positive or negative? How to determine? We have this key. Okay. We have this key. So the asymptote is actually our guide in this sketching curves. Okay. So we can take this, because our graph will not be touching those asymptotes. We can just write down that this is negative 1, this is 1, right? So imagine that there is a particular asymptote here, right, in the negative 1 and 1. So we can take numbers in this interval and check it through here, and check whether they are positive or negative. So we know they will concave upwards or concave downwards. Okay? So maybe checking with the, let's say 0, checking 0. It's a negative, right? Because the denominator will be negative. Okay. So we are only checking the denominator because the top one, the equation here, is always positive. Okay. So check 0, it's negative. Check with maybe positive 2. It's positive. Checking with the negative 2. It's become another positive, right? So we can make sure that this is positive, this is positive. So the positive one is concave upwards, the negative one is concave downwards, this is concave upwards. Okay. And with all those statements, now we can try to sketch using our guides. Okay. First, we can draw the asymptote, draw the line, and then we draw from the left interval that is increasing. So let me go through the sketching curve. Let me draw here. So first, drawing the asymptote. Let's say the asymptote is here, -1, and okay. That's the vertical asymptote. We have horizontal asymptote. We have horizontal asymptote at y equal 2. So we need to also draw that. And make sure that we are going through all those guides. Okay. So this is 1, 2. Let's say this is the horizontal asymptote. Okay. So this is y equal 2. This is x equal 1. X equal -1. Okay. Okay, now look, let me zoom out a little bit. From 0, or from the negative infinity through -1, we need to have an increasing. So the most possible sketch is, okay, make sense? Let me make it a little bit longer. Maybe here. Okay. So this will be okay, like that. Now, of course, we can also check that this is a concave upwards. Concave upwards. So this is concave upwards, right? And then the middle interval, the middle part, we have intercept 0, 0. So we need to make sure that our graph is at 0, 0. So this is 0, 0. And from the first derivative, it's going to be increasing, decreasing. Okay, increasing but decreasing. So the most possible way is to make it going through here and decreasing here. And then the last part is going to be decreasing and concave upwards like this. think that's still okay. So this is concave downwards, concave upwards. So this is our local max, the 0. Maybe any questions first? At least this will be one of the typical question in exam. So any functions, you need to do this, all this stuff. You can directly derive first derivative, second derivative, checking their line numbers. It's okay, and then checking the asymptote, checking the other things. But I think asymptote can be very tricky. So my suggestion is doing that first. To make sure that when this happens, this asymptote will have our line numbers. So it has no inflection point. No inflection point. It has asymptote, but it has asymptote where the complete change, but it's not inflection point. It's asymptote. I think for practice at home, you can try using calculus and then try put the function into the graphic calculator to the website and see the graph, whether it's similar or not. I think it should be similar like this. Okay. If there's no question, let me give you one more. The one that I give you, I think, at last week. Let me go through one more. The functions is so sketch the curve. Okay. Now there is something interesting when you try to do this sketching. When you're trying to find a critical number, you will not find any critical number. So that's quite interesting. Okay. So, but still we are still able to draw the sketch, the curve. Okay. So first, maybe let's just check the domain. That is quite obvious that x is not to be 0 and x is not to be equal with 1, right? And I think for other part of x, it's still okay. So we still can say that other element is a real number. We can check the intercept. Taking the f of x equal to 0. So we are going to solve this algebra. So taking the x squared, x minus 1 squared, x minus 1 squared minus x squared. So this will be around x squared minus 2x plus 1. X squared will be cancelled, so it's still negative x plus 1. So x is, or negative 2x is equal negative 1, so x equal half. So at half 0, this will be an intercept. And there is no intercept when x equals 0 because it will be undefined. And then asymptote. First, we can check the limit. Maybe we can check the limit for the horizontal asymptote first. So x is going to be positive infinity or negative infinity. You can write both, but I will just write one here just to simplify my process. So we can write down and separate this. And we know that this will equal to 0, right? This will equal to 0. So y equals 0 is our horizontal asymptote. And for the vertical asymptote, based on our domain, we can check the x close to 0 and x close to 1 as our limit. So we can check those vertical asymptote as well. So let me write first is x closing to 0. You can write, or maybe checking left and right side. But I think it should be okay for both cases. And it's going to be an infinite number, right? And the same thing with the x close to positive 1 from left side or right side. Oh, squared. This will equal to negative infinity. So x equal 0 and x equal 1. This will be a vertical asymptote. So we've done the domain, intercept, and asymptotes. Okay, the next part is we are going to do calculus part, which is the first derivative and the second derivative. And sometimes since it is having a separate equations like this, actually it's up to you. If you want to make it like one big fraction like this and then derive, still okay if you want that. But I think I will just keep this separate and then derive each equation. I think it's much simpler, maybe faster, and maybe that's one way to avoid mistake. Because if you derive this, I think it will make many mistakes, especially if you are running up. You have a time limit, and you need to make sure that this is going to be derived completely
Okay, the derivative is not really the final answer, but this is just an observation, not really a complete answer. I think I will just keep separated and then derive each one.
So the first derivative is 1 over x squared, derive. You can imagine it's x with power of -2, so -2 go to the front. -2, -1 is -3, so it will be -2 over x cubed, right? And then the same thing for the other equations. It has negative, multiply with negative, so it should be +2 over x minus 1 cubed. Okay, we need to check whether this can be equaling to 0 or not. And I believe some of you already try, and we don't have any critical point here. But anyway, let's combine this all together. So x cubed. So -2 x minus 1 cubed plus 2x cubed. So we can check that this is going to be -2 x cubed, -3x squared plus 3x minus 1. So we are going to have 6x squared -6x plus 2 and over x cubed okay. Now if you look at the quadratic here, you can directly go to checking the we call the discriminant, checking the D discriminant. Discriminant is one part on your quadratic formula that is stated by b squared minus 4ac. So we can check this, and we know that from our coefficients, this will be 36 minus 4, 6, and 2. So we are going to have a negative, which is not a real number, right? So it's an imaginary number. So there's no real numbers that satisfy this quadratic equation. So so when we take this, let me write equal to 0, there is no critical point. Okay. And again, because we already have the asymptote, the vertical asymptote, which is 0 and 1, we can also check that in our line number. To check our f prime, to check the interval on the f prime. Okay, so we can do that. So we check the line number and checking the 0 and 1. Remember that this is a vertical asymptote. So we can check -1. We can check -1. The top equation will be positive. The denominator will be also positive, so this will be positive, right? So check -1 and check maybe 1/2. 1/2
1 over 2 here will be negative. 1 over 2 is positive. Still positive, still greater x squared from here. So it should be positive and negative, so it should be negative. Negative.
And then check 2 is also positive, I think, right? So it will go increasing, decreasing, and increasing. So although there is no critical point, we still be able to check whether the function is increasing or decreasing. Okay? If the question is asking the interval, don't forget to write the interval. Okay? So maybe increasing, f increasing on and decreasing okay, but the real problem is the second derivative, because we are going to solve big polynomial problems. You can imagine now we have the cubic, and if we derive one more time, we have the fourth, right? Polynomial with degree 4. But I think still, in our level, in university level, this still can be able to solve. With your level also, this still can be solved. Although it takes time, really takes time. You need to write a really long process, especially for the first derivative and second derivative. Okay, so we take the second derivative, and again, I prefer to derive with the separate equations rather the full fractions like the one that we show in the first derivative. So negative 2 over x cubed, we derive, it's become 6 over x with power of 4. And this will become negative. It's 6 over x minus 1 with power of 4. Okay, and then we need to multiply this. Okay, we need to check. Okay, then we need to solve whether it has a root or not. I think for some students who takes my basic math, you will remember how to solve this polynomials. Okay, for the if you don't remember how to solve the x minus 1 with power of 4, if you don't know how to expand this is precisely goes by the coefficient will be 1, 4, 6, 4, 1, right? If I take it from it goes from we call it Pascal triangle, right? So this is for the coefficient, but the result is x power of 4 plus 4x cubed minus 6x squared plus 4x minus 1, right? So a squared, b squared, a squared, a cubed, b, a squared, b squared, b cubed, a, yeah. And then a fourth and then b fourth for the rest. And then multiply with 6. Well, we could do this 6 And then we can factorize this 6 also, so we can write this is negative x4. So we can cancel this. So we have so now if we want to equaling this to 0, then we are going to consider the polynomial equation px okay. Some techniques in your polynomials will be very handy, very useful here. Okay. But I need to go faster within this polynomials. To find the polynomials, first you can check the possible root. It's from this divided by this. So factor 1 divided by factor 4. This is plus minus 1. And then plus minus 1, plus minus 2, plus minus 4. Okay. So we are going to have possible roots are plus minus 1, plus minus half, plus minus 1 over 4. So only 3 kinds of root that we might have that we need to check. Okay. And then to know how many positive root or negative root, let me give you one suggestion. It's called the Descartes rule. So if you take my basic math, I suppose you are already familiar with this method. So this is positive to negative, so 1. Negative to positive, this is 2. Positive to negative, this is 3. So whenever there is variation of change, it's going to have our possible number of roots that we have. So it has 3 variation of change, which means we are going to have 3 positive roots or 1 positive root. How come we have the number 1? Okay. In this method, you need to minus with 2. Okay. This is not calculus, okay, by the way, not on your textbook. This is just a supplement, okay, if you want to have another techniques. Okay. So this is for the positive root. The negative root, we need to plug in the negative x. So we are going to have negative 4x cubed, negative 6x squared, negative 4x, negative 1. So this is going to be all negative. So no change. So we don't have any negative root, which is helpful. So we are going to check the possible root from here, only the positive one, only the positive. Okay. And how many root that we might need, because we have the cubic, so we will have 3. Okay, 3 root. Okay, so the next is we are going to use the syntactic division. Okay, syntactic division. And maybe try from 1. So 4, negative 6, 4, and negative 1. 4 goes down, and 4 will be multiplied with 1, and put here another 4. Plus this is negative 2. The same thing, multiply with 1, negative 2, 2. So it still has the remainder. So it's quite interesting here. We say that we might have 3 positive roots or 1 positive root, but we don't have negative root. But we have only 3 options. If 1 is not possible, there is 2, which means that we don't have 3 positive. We only have 1 positive. Where are the other 2 roots? Probably an imaginary or complex root. Okay, that's the possibility. Okay, we check another one. We check maybe 1/2. Okay, I think we got this. So when it's 0, then this is our root. So this is our root, positive root. So if we build a table to help us to understand, so let me write this as a positive root, negative root. So we may have 3 or 1, right? And we have no negative root for both paths. So this is A, B, let's say. And then we have total should be 3, but we still have some complex imaginary number inside. That should be 2 to make it the total 3. So this is how we observe polynomials. So when we try to find roots in polynomials, okay, we might encounter with something like this x cubed. If you can factorize, that's okay. But if this is something that it cannot be factorized easily, this is some method that I can suggest. So you can check from the possible roots and maybe narrowing through the positive and negative root. This is not really obligatory, not required. If you can check from all this, I think it should be still okay. You can check one by one. You can still find the root. You can still find the roots. But at least we find one root. And we still find, maybe this will be this b, in this b. It has one root and complex conjugate. It has complex root. Okay, I think we need to continue after the break. Okay. Okay, we are going to have break and continue. Okay, we are back to this question. So just one point here. This point here is whenever you find in higher polynomials, and I do think if this is coming up in your exam, it will be really trouble, right? So first it's like take really long time to process. And then there will be mistakes that might happen, especially when you're doing this, okay, this derivative. This is just want to show you. First is sometimes there is a curve that they don't have any critical point. It can be. Now, from this part, what we want to looking for is just this x equals half, which is if we take this out, and we know that this part is not factorizable, which means that the only conclusion from here is x equals half, probably our inflection point because it's equal to 0. So let's check this x equals half in line number. Okay? So that's the important thing for our calculus. This other part here is just additional. So let's try to take our line number and put half. And also maybe put the 0 and 1 as our vertical asymptote. And then we need to check, let me write the second derivative equations. Where is my second derivative? There. So f double prime is 6 over x4 Okay, let's check the interval. Okay. We can check -1 for the left part. -1 is possible. But it will be positive. But it will be 6. How about this? So it's still greater, the left is greater than the right. So it's still positive. You don't really care much on how much is it. So it will be positive. So maybe take 1/4. Okay. 1/4. The left part, because it's 4 with power of 4, this will be really great, really high, really huge. And 1/4 here, I think it will be going to be less than this part. Okay, because it will going to be having, at least this is going to have 3/4 with take power. Yeah, it will be less than this part, still less. Still less. Yeah. So still positive. And then between half and 1, maybe take 2/3. Now this is will be, we need to check. So 16/27, 16/27, so 27. Now the left is less than the right? If you think about it. So it should be negative. And if you check x equal 2, if you check x equal 2, it will be 6/16 minus 6, which is negative, right? It's negative. Okay? Which means this is going to be concave upwards, concave upwards, concave downwards, concave downwards. Okay. Okay, let me write all the line numbers that we find so far. Okay, because I have no space here. Let me put another page just to write the conclusions that the f prime so f prime, we have 0 and 1 as our vertical asymptote. This is positive, negative, positive. And we have negative, positive, positive, negative, negative. Okay. Okay, we translate this f prime and f double prime into our curve. Let's say this is x equal 1. And this is half. And then the horizontal asymptote is on the 0, and vertical asymptote, another one is x equals 0, so it's on the x-axis and y-axis. Now first, maybe naming this 0, 1. So first, looking at this f prime, we should have an increasing from negative infinity to 0. So we are going to have something that goes up. Okay? But is it going to be like this or like this? Because it's asymptote, it's supposed to be having like this, right? And it is confirmed by this positive. This is concave upward. So we have to be having this, like this. So we are going to have that. So that's the first step. Taking the curve to take this, going to be there. Oh, by the way, I forgot to write that this because concavity change, then x equal 1/2 is inflection point. I forgot to write this. Okay. So now, from 0 to 1, it's going to be decreased. So you can imagine that it's going to be like going down like that. But how the curve will be, it depends on the concavity. So first has concave upwards. So maybe it's going to be like this. And maybe somewhere in nearby this top, it stops here, and then going to be concave downwards. Okay? And I hope that makes sense. Okay? So this is concave upwards, and this is concave downwards. And then the right part, we are going to have an increasing. So we are going to look at that. It has like this direction. But it's going to be negative in the secondary. Yeah, so downward. Okay. Again, concave downwards, and this is an inflection point. Let me write inflection IP. So this is a vertical asymptote, and this is horizontal asymptote. Okay. Just for sketching this curve, we have a long way to go. Really long process. But I hope you can take the conclusion how we are going to be able to solve or sketching this curve is basically observing this f prime and f. How we can get the interval if we don't have critical numbers? We can use the asymptote as our guideline. Okay, I think for another curve example, I believe I can give you as exercise. Okay? As exercise, I will continue this chapter 4 with another sections. It's the indeterminate forms and L'Hopital rule. Okay? So let me put some line here to take this as a finished part. So this is 4.4 indeterminate forms and L'Hopital. So why this L'Hopital suddenly appear in chapter 4? I suppose this is about the application of the derivative, which is one of the application is sketching the curve and taking the L'Hopital. So we will have the indeterminate form in limit. So we will have a limit problem. And how to solve that limit problem is one technique called the L'Hopital. So let me give you some idea. Okay. Maybe consider f of x is a quadratic equation. Let's say x squared plus 3x minus 4, and function g of x is a logarithmic natural ln x. Okay, now if we take, for example, take the limit, if we take the limit as x approaching to, let's say, maybe 1, okay, x approaching 1 of this f of x, let's say over g of x, this will be going to have 0 over 0 situations, right? This is what we call the indeterminate forms. Okay. In chapter 2, if you remember, when we have this 0 over 0, we need to either factorize if it is a polynomial, or maybe using trigonometric identity if it is a trigonometry, or rationalizing, or if it is a conjugate with a square root something, right? But the other way, okay, if this happen, is we are going to have the L'Hopital rule, which is, I believe most of you already know that. The L'Hopital says that whenever we have the 0 over 0, we can take this limit and we can derive the numerator and the denominator. So we are going to have this, right? But how is this possible? How this technique appear suddenly? So let me give you an example through my example from the left part, the functions. Okay. So let's draw first. Let's draw first the functions. Okay, if we have from 0, 1, let's say it's negative 4, because we will have, if we factorize this will be plus 4 and negative 1, right? So this should be negative 4 and 1. So 1 is here. Okay. And 3 over 2 is our minimum value. So negative 3 over 2 is here. Let's say that is our graph. So this is for f of x. Okay. For ln, we are going to have for G is going to cross this x equal 1. Okay, maybe that is our, maybe make it more smooth. Okay. Let's say this is our g of x. Okay. If we zoom in into this area nearby x equal 1, okay, if we zoom in and zoom in and zoom in, so let me write when x is near 1, f of x over g of x if we can split the f and g with some small segments, okay, we cut all of them and make it as small segments like this. So let's say, let me maybe with purple, so that's small segments. So small segment for f, let me write a triangle like that. So this will be, we call df. Okay. And this will be dx. And for the g, let me write another segment, small segment, that we call, this is dg. And it's the same dx, small dx. Okay. Now, okay, if we think like imagine that this is a really small sections here and here. So df and dg. When x is near 1, we can write that the function itself is representations of our df over dx. And g is dg over dx, which is a representation of our f prime x and g prime x. Okay, to be precise, what does it mean is if you close this this area, if you zoom in, you will see that at nearby the x equal 1, the function is kind of like straight line, right? Like a tangent. Okay? If you remember what is the tangent, it's related to the first derivative and so on. Okay? So let me take you another picture. So for this part is more general functions. Maybe here. Okay, I hope I can write something here. Okay. So let me write some notes about this rule. So we call this as a L'Hopital rule. But actually, the one who found the rule is not L'Hopital, but the name is L'Hopital. Do you know why? And this is just FYI. Do you know the Bernoulli, the guy who in physics? He is actually the one who found this L'Hopital. But L'Hopital has money, so he sponsored, he invests, but he is using his name. Yeah. Yeah. So the L'Hopital, so let f of x and g of x. First, they need to be differentiable. And continuous. Continuous. And 2, at x equal to a, f of a is equal to g of a is equal to 0. Three, g prime a should not be equal to 0. So if these 3 options or these 3 requirements has been fulfilled, we can write limit, and sometimes in the process we are going to write that if we write this LH like that it means that we are doing some L'Hopital, which means that we are simplified this f will become f prime, and g becomes g prime. And we can do as many as we want. Okay, if f prime and g prime still in 0 over 0, we still can do another L'Hopital, as long as satisfied and find the solutions. But remember to check the limit if it is 0 over 0, okay? Or infinite over infinite, that's also possible. Because 1 over 0 is infinite. Okay? So infinite over infinite also can be possible. So this is we call the indeterminate form (0 over 0) or infinite over infinite. To give you a little bit proof for this general L'Hopital rule to be true, we can take our times just to let me write on the left so we still have some space. So limit so let me write because f of a and g of a is equal to 0, so I think it's okay if you just write f of a like this and g of a like this, right? Because they both are 0. And we are doing multiplications 1 over x minus a and 1 over x minus a, right? And if we think clearly from these equations, we are now having fx minus f of a over x minus a and g of x minus g of a over x minus a, in which these two are definitions for derivative, right? The limit definition for derivative. So we can say that this is going to be f prime x g prime x, and with that, supposedly that we can substitute a to the x, and we have our final solutions. So this is limit definition of derivative. So whenever you find forms of limit that is 0 over 0 or infinite over infinite, you can derive the numerator and denominator. Okay? And you can derive as long as you want, as much as you want, so that you can find the equation that's satisfied with limit. Okay? So this is the first case, okay, the first indeterminate forms. We have at least four indeterminate forms. To still have, okay. I think giving you an example here, just maybe really simple functions for the limit. So if you have the limit as x approaching infinity, let's say ln x over square root of x. If we check, this is going to be infinite over infinite, right? So we can directly derive both equations and writing LH as the L'Hopital. So we can write, so limit, the top equations will be 1 over x, the bottom one will be 1 over 2 squared of x. So we are going to have limit, this is 1 over x, 2 squared of x, and then we can cancel the x and square root of x, and then take another square root of x down there. And we know that when we plug in the infinity, it will be 1 over infinity, right? So we are going to have 0. Okay. I think I will go for one other case, and then the rest will be, I think, tomorrow. Okay, the next forms. The next form is called the indeterminate products. Okay. This is when we have, for example, let me just give you an example. If you want to go back to the previous page, I will do that later, okay? But please pay attention for this one first. So if we have this limit, this will have 0, and when we put 0 to ln, this is going to be infinite, right? So this is what we call the indeterminate product. So when we have 0 multiply infinite. So what do we do? The essential for all this method, for all this so-called the indeterminate forms, the idea is to force the equations to be in forms of f over g or 0 over 0. Okay. So when we have, let's say, f multiplied with g, we need to make this f and make it into this form, okay? Or maybe this form. So for example, in our case, if we take this, if we change the way we write, let's say ln x is on the top and 1 over x is on the bottom. It's the same thing, right, as the original questions. But now we have, this is 1 over 0, infinite, this is also infinite. So it is indeterminate forms infinite over infinite, in which we can do a L'Hopital rule. Okay, so we can do L'Hopital rule here. So take the L'Hopital and then make it into ln x become 1 over x, and the bottom part is negative 1 over x squared. And we can cancel this x, so we have limit, sorry, I forgot to write the limit. Limit as x approaching 0 from the right of negative x, which this is also 0. Okay. So I will, I think, stop until here. Do you need to look on the previous page? Or, okay? If you need to look the last page, let me know. Okay? So there will be 4 cases. So the first one is the original one, the 0 over 0 or infinite over infinite. The second one is this, the product. The third one is we have subtraction. So the infinite minus infinity, that is indeterminate forms. The last one is the indeterminate powers. So that is when we have the 0 with power of 0 or infinite with power of 0. Or 1 with power of infinite. 1 power of infinite is not 1. It's something else. But in limit, okay? In limit. Okay? In limit. If you talk about the 1 with power of really high numbers, of course it's 1. But in limit, it will be an indeterminate forms. Okay, if I have more time tomorrow, I will let you know how to define that forms. Okay. Yeah, because it's interesting. Okay. Interesting. Okay, and then The rest will be tomorrow, and also for more example for the L'Hopital rule. Okay, any questions? Any questions? I think I will attach all the answer key. I think by today after I upload the class recording. So first is the homework answer key and the midterm, the last year midterm. Of course, some parts maybe like optimizations or maybe this L'Hopital, not really sure, but you can try first. You can try. Because I think for the L'Hopital and optimizations, some of you I think already learned at least the introduction in high school, at least. If no, then yeah, it's the new thing. I think some of you already learned that.